Imagine a sky ablaze with shimmering curtains of light, dancing in vibrant hues of green, pink, and purple. This breathtaking phenomenon, known as the Aurora Borealis in the north and Aurora Australis in the south, has captivated humanity for millennia. It's more than just a beautiful display. It's a direct connection to our star, the sun. For centuries, these lights inspired myths and legends, from spirits dancing to divine messages. Today, science offers a profound explanation, revealing an intricate cosmic ballet. Understanding the aurora means understanding the fundamental forces at play in our solar system. Our story begins 93 million miles away, at the heart of our solar system, the Sun. This colossal star is a giant nuclear furnace, constantly fusing hydrogen into helium. This process releases immense energy, not just as light and heat, but also as a continuous stream of charged particles. These particles, primarily electrons and protons, are ejected from the Sun's upper atmosphere at incredible speeds. We call this outflow the solar wind. Sometimes, the Sun experiences more violent eruptions, like solar flares or coronal mass ejections, sending even larger bursts of these particles our way. As this solar wind races towards Earth, it encounters our planet's crucial defense mechanism, the magnetic field. Generated by the molten iron core deep within our planet, this invisible shield extends far into space, forming a protective bubble called the magnetosphere. It deflects most of the harmful charged particles. Without this magnetic field, the solar wind would strip away our atmosphere, making life as we know it impossible. It acts like a giant cosmic umbrella, protecting us from the sun's constant bombardment. This shield is vital for our planet's habitability. However, the magnetosphere isn't a perfect, impenetrable barrier. At Earth's poles, the magnetic field lines converge, creating weaker points. Some of the charged particles from the solar wind are funneled down these lines, bypassing the main magnetic shield. These particles are drawn towards the magnetic poles, where they gain speed and energy. This is why auroras are predominantly seen in high-latitude regions, forming an oval around the magnetic poles. It's a direct consequence of our planet's magnetic geometry. Once these high-energy particles enter Earth's upper atmosphere, they collide with atoms and molecules of gases like oxygen and nitrogen. These collisions excite the atmospheric gases, causing them to temporarily gain energy. But excited atoms don't stay excited for long. To return to their stable state, these excited atoms and molecules release their excess energy in the form of light. This process is identical to how a neon sign works, but on a grand planetary scale. Each gas emits light at specific wavelengths, creating the aurora's distinct colors. The most common auroral color is a vibrant green, produced by oxygen atoms at altitudes of about 60 to 150 miles. Higher up, around 150 miles and above, less frequent collisions allow oxygen to emit a rarer red light. This red often appears along the top edges of the green aurora. Nitrogen molecules contribute to the purples and blues, especially at lower altitudes. The specific colors and their intensity depend on the type of gas, the altitude of the collision, and the energy of the incoming solar particles. It's a dynamic, ever-changing palette. To experience the aurora, you need dark, clear skies away from city lights and a location within the auroral oval. This typically means regions like Alaska, Canada, Scandinavia, Iceland, and Siberia in the Northern Hemisphere. The Southern Hemisphere has its own aurora, visible from Antarctica and parts of Australia and New Zealand. The best time to see them is during the long, dark nights of winter, especially around the equinoxes. Solar activity also plays a crucial role. Stronger solar winds and coronal mass ejections lead to more intense and widespread displays. Earth isn't the only planet to host these spectacular light shows. Jupiter, Saturn, Uranus, and Neptune, all gas giants with powerful magnetic fields and thick atmospheres, also exhibit auroras. Their auroras are often even more energetic due to their stronger magnetic fields and different atmospheric compositions. Studying these extraterrestrial auroras helps scientists understand planetary magnetospheres and atmospheric interactions across our solar system. It reminds us that the universe is full of wonders, many driven by the same fundamental physics we observe here. The Aurora Borealis is a profound reminder of our planet's place in the cosmos. It's a visible manifestation of the sun's power, Earth's protective shield, and the intricate dance of particles and fields. It connects us directly to the dynamic processes occurring millions of miles away. Next time you hear about the aurora, remember the incredible journey of those tiny particles. From the fiery heart of the sun to the shimmering curtains in our polar skies, it's a story of cosmic forces, a breathtaking display of nature's grandeur.